My name is Rico. I'm a colleague of the presenter, Chris Wong. He and I both work at a company called Query, which will come up a little bit over the course of the conversation. So disclosure that we work there. I'll let Chris introduce the scope of today's presentation, the project that inspired it.
Basically, as Rico said, we're going to talk about this project, which has been an ongoing, not terribly focused effort to build a spatial data set of New York City capital projects. So I'm going to give an overview of the capital budget because it's pretty complex, all the different nomenclature and abbreviations and names of different things and the cycle that it comes out on. A look at existing information and resources available for the capital budget. We're going to look at our crowd geocoding effort, which we've been running since November, but it's stalled a little bit lately, except for tonight, where we're going to kick it back off and you all will actually get an opportunity to geocode a few projects if you so desire. So after the presentation, we're actually going to divide and conquer, and you'll be able to take a small list of 5 projects and see if you can help look them up. And that'll actually end up right in the data set, which will be pretty cool. So before I go further, I'll show this map. Basically, this is the downstream product of what we've got so far. And you'll see in the little information window on the left, this is showing about 2010 projects out of a data set that has about 5,000. So it's definitely not complete, but it is close to complete for a small subset of the data, which is all what we're calling local projects. And I'll explain what that means in a moment. But each of these circles represents one row in the data set of capital projects that are currently ongoing in New York City. And if you hover over them, RC of Jesse Owens. Okay, this is a playground that costs $7.5 million. This one is a cultural arts center that costs $7.8 million. This is heating and cooling replacement. So lots of different capital projects going on throughout the city. So NYC's capital budget provides funding for construction and rehab of infrastructure such as schools, roads, libraries, and parks. Projects must have either a value of $35,000 and a period of usefulness of at least 5 years.
Yeah, earlier in the day when we were talking about this, Chris, you had said it was an and.
Yes, I think that's correct. And then capital budget is funded by proceeds from these various different sources. So this is all on this FAQ page. So I'm definitely no expert on capital budget. This is just kind of something I've studied over the years, and I also worked on it in some semi-official capacity while I was working at the Department of City Planning on the capital budget team a few years ago. So very interested in where these things happen and how much we spend on them. And we're just scratching the surface of what's possible if we can generate a good spatial data set of these projects. So just so you can get a rough idea of what we're talking about here, this fiscal year's capital budget is about $11.8 billion. So it fluctuates over time, but every year they do a preliminary and then they do, I think, a couple of rounds of that. And then there's finally the approved budget. Just some nomenclature that you might see inside of capital budget. What you would consider a project is at the bottom of the list. And the capital budget itself, the official document that comes out, the Office of Management and Budget, has project types. So that's the top level. So these are like 2-letter codes, describe very top level of project. So LB means Brooklyn Public Library in the examples I'm citing here. Then there are things called budget lines. So basically the capital budget shows project types and budget lines. And here's a couple examples where these are almost identical, but one is for construction, reconstruction, rehab, improvements, site acquisition, et cetera, for branch libraries in Brooklyn. And then the other one is the exact same thing, except that it's council funding, whatever that exactly means. But at the bottom of the hierarchy is projects. And what's important to know about projects is that it can be funded by multiple budget lines, not just one. So you may find a project that actually is pulling money from 2 buckets, which is what the budget lines are. So when you actually go to the website to download the capital budget, and I'll show you the website very quickly, but this is a New York City government site. Inside here, under June 2020 adopted budget, you will see a thing, if you scroll down, that says capital budget. This will download a many 100-page PDF, and it looks like this. So this is one little page, but it looks like a screen dump from a computer system. And each one of these sections is a budget line. So there's a budget line with an ID. So this is HB 1027, for example. So HB stands for highways and bridges. So that's like the top level project type. And then this one is for reconstruction of the Harlem River Drive Viaduct from East 127th Street to 2nd Avenue, Manhattan. So that sounds like a project, but it's also a budget line. So maybe there's several projects underneath that. So that's a lot to go over and gives you these kind of big high level numbers, but most of these are buckets of money. They're not terribly specific about what they're actually going to spend it on. So then there's another thing called the Capital Commitment Plan, which is released 4 times a year and includes the actual project level details. So this looks like another set of screen dumps from a computer system. And inside here, we've circled one project. But I think the caveat here is that this is one project and only the elements of that project that are funded by a specific budget line. So if a project line shows up, if a project is funded by 2, it'll actually show up twice in this document. And this document's 4,000 pages long. and is actually so large that it's published in 4 sections. So I'm going to go back to this website just to show very quickly that if we scroll down to Capital Commitment Plan and click on it, you will see that it's actually published in 4 volumes because it's so big. So each one of these is a PDF. So if you wanted to search for a project, you'd have to download all 4 of these, open them up, and Command F or Control F. And I think some people who work in government do this from time to time in order to find details about a project. So that's how things had been for the last little while. And when I left city government, this was all we had to work with versus anything else we could beg, borrow, and steal from other agencies or negotiate getting our hands on. But this is the only official public record of how we spend our capital money that's official and detailed enough. But in the last few years, another publication that's come out called Capital Project Detail Data, which is wonderful. This is kind of another set of PDFs on top of the original ones, but these are divided by borough instead of just being 4 chunks that are released in order. Basically, they've made a nicer presentation for this information. So we have 1 page for each project. So here's the same one that was listed here in this screen dump that was kind of a little hard to read for Carroll Gardens HVAC replacement is now shown here. So this is the same project. You can see project ID has a nice little alphanumeric code, LBM 13CGHC. But this has lots of goodies in it and it's much better formatted. So we can see the 2 budget lines that fund this. So here are the 2 budget lines. We can see the original budget, and this is in thousands. So this is a $1.1 million project. Then we can see what's been spent already and what's planned. So for this original budget of 1.1 million, we've already spent 1 million, and we're planning in fiscal year 22 to spend another 3 million. I don't know much about the details of this project, but the total, if you combine what has already been spent with what is planned to be spent, is about $4 million, which is very much different than the original budget. So I won't opine on why that is, but those 2 numbers are very different. So we should maybe check that out. So this is great. And when I discovered this last fall, I was like, we've got to have this data. So we ended up scraping it, which is wonderful. And it also has this community board served field. And I think there's actually, at least in the ones that were published last fall, a big typo or big error in them where I think they reversed Bronx and Brooklyn because this is supposed to be 306 instead of 206, but we fixed that in our data. So we end up scraping it, even though there is a data set available on New York City Open Data for this now. And actually revisiting it a few months later, it actually looks like they've improved that data set because first time we looked at it last fall, it actually didn't have a lot of the fields that were contained in the PDF. So as part of revisiting it before this presentation, I realized that they have improved the data set. So I'm going to show at this point what it looks like. So this is capital project detail data $, which is on the New York City Open Data Portal. And just so you can see, each one of these is a capital project, and you can see the project IDs here. You can see this is the community boards field, which I think is called community board, and you can scroll all the way across and here's all those numbers for what was actually spent, this is the original budget amount, etc. We also have our version of it, which is on query.cloud, which is what we scraped. Someday I would love to compare these 2 and see if they actually jive, which they should, because they're in theory pulling from the same source, but you can use either one of them at this point, and I would love to combine the efforts at some point and just check and see if the city's official one is worth using at this point. It seems like it is, which is exciting. So getting the data, basically this is a little table that if you group everything by its borough and then sum the combined total and the prior actuals and the planned spending, this is what you end up with. So 36 billion of already spent plus planned spending for citywide projects. And then the rest of them fall into a borough. So that's an important distinction because they actually do distinguish between what is considered a citywide project, which I guess means it would have citywide benefits versus borough benefits. Then there's this concept of local. So there is a community board served field and it's not filled out for everything. So there are some projects that are assigned to the borough of Brooklyn or the borough of the Bronx, but do not have community boards listed, which we would consider borough-wide. So the ones that do have community boards listed may have 1 or more. And that's basically saying these communities will benefit at least directly from this project. In Brooklyn, for example, many of the ones that are in Prospect Park list all of the community boards that are surrounding Prospect Park. So I haven't done a whole lot of research into how accurate that is, but at least it's there and it's something to work with. So this is just a quick breakdown of what we're calling local versus borough-wide for all the non-city projects in the data set. So you can see the spread is a little bit different across the different boroughs in terms of actual funding amounts. So on top of that, because we have this community board served field, we were able to do some simple mapping. So we don't have like discrete geometries for these things yet, but using those fields, we know where community boards are or community districts are, so we can actually combine them and do some aggregations. This was just taking the 10-year capital plan category for each one of these projects and just grouping or aggregating the total spend by community district. It yields these little small multiples maps, we call these. So each one of these shows a different category and where the spending for that category is listed as happening or at least listed as supporting in the data set. There's actually a much longer version of this that has many more of these. So this is just kind of the top chunk of it that would fit on a slide. But I encourage you to go check out the blog post that we wrote on this last fall. And you'll notice that things like this one, which says neighborhood parks and playgrounds, has coverage all over the city because those are everywhere. And then there's some that are much more specific to some other kind of work that are only happening in a few places or one place, which is mildly interesting, but I would encourage you to go check it out. Each one of these could be its own little research project because there's so much going on here, but interesting way to check out the data. So moving on, we want to go below community district level. And the old saying is everything happens somewhere. The task at hand is assigning geometries to these projects. Interestingly, this is not the first time that this has been approached. And I've seen Councilmember Brad Lander, for example, actually has a web map of capital projects on his website. And that's the work of his staffers or somebody in his office that's actually pulled out all of the projects that are relevant to his district, geocoded them, added additional information, and made like a nice web interface for them, which is wonderful, but it doesn't apply to the whole city. There were efforts while I was in city government to do the same thing, but they never really saw the light of day, which is why we have to do this again on the outside as a community project. There's a lot of different efforts to try and figure out how we can add a spatial component to these capital projects. Can we assign point geometries to them? Well, we can try. So there's 5,000 of these things, but if I just look at the local projects, so the ones that list, for example, Community District 6 in Brooklyn, which is where I live, I would say that it ends up being just a few dozen. So it's not that bad. I can sit down for an hour and a half and actually read the project descriptions and try and locate each one of these things. So this map comes with a huge asterisk because a lot of these are sewer projects that cover very large swaths of space, but with the caveat that we just want to have some notion of where it's happening with single point geometry. This is the best effort of doing that and gives you this very interesting picture of where the big ones are, where the little ones are. And you can see there's things here like William Penn Playground renovation, $800,000. There's things that are in the middle like Red Hook Ball Fields, $15 million for a ball field project. There's the Brooklyn Cruise Terminal, $3.5 million. Then there's big ones like this one, which I believe is a sewer or some kind of water project, which is reconstruction of Columbia Street area, phase 2. So lots of codes in here, lots of little interesting tidbits, lots of interesting stuff in Prospect Park, like reconstruction of the carousel, reconstruction of the picnic house, things like that. All these Prospect Park ones also listed Brooklyn CD6, but they also listed probably all the surrounding districts as well. So we have a little bit of overlap between districts that may show up here.
And were these manually annotated was Jim's question.
No, sorry, it depends on what you mean by annotated. These were manually geocoded, so I just had to choose what I thought was the best point to place the marker. But the actual text that you see on the screen here is pulled straight from the data set. So it's what's officially in those PDFs as a project description.
Cool, thank you.
Okay, great. Now do the whole city. Okay, so we have 5,000 of these projects. I'm gonna need some help. So if you know me, I'm on Twitter a lot, but this is me saying, hey, I need volunteers to manually look at projects to add lat-long coordinates. Pretty straightforward. If interested, I'll assign you a community district and each has several dozen, should take a couple of hours. Who wants to help? So I just kind of fired this off and said, it'd be neat if a few people jump in and help me out with this. I don't really know how I'll manage it, but I'll figure it out. And people started responding and saying, hey, I'll do it. And this person, Dante Lee, I love his Twitter name, This Guy Maps. He jumped in and I think he did more than one actually. Basically, people were just excited and they were like, hey, I finished up this district that you assigned me. And I'll be like, okay, you want to do one more? And they're like, sure. So a bunch of people were repeat helpers that did a lot of these. And basically we've gotten up to about 2,000 now, which is very close to complete of just the local projects. So keeping things organized, we use an Airtable. Basically, I create a view on the sidebar. So BK01, BK02, BK03. I would give someone a community district and then they can click on this and have just their list of projects that they're responsible for. And then all they have to do here is go in and look at the scope summary, look at the description, see if they can find it on Google Maps, and then drop a lat long in here. So we're good to go.
Was all this mapped in ArcGIS? How did you map the sewer lines against funding, especially since they may run across so many different areas? And I think you might have covered this.
Yeah, it's not that sophisticated. So I think it's much more just trying to find the general area. I glossed over a big chunk where we did programmatically geocode a bunch of these. There's an existing data set for some capital projects that is published by Do It. It's on a web map. And I pulled those down and got centroids for those. And that was, I think, a few hundred projects that were just kind of bulk geocoded that way. But most of these were done by the community. So by our powers combined, so what we're doing here is on the right, which is this lookup table. So it's geometries for each project provided by volunteers. And then we join by project ID to the official data. Those two things together make a spatial data set. It's obviously not perfect and it's obviously not complete, but we've made a lot of headway and we're trending towards a complete data set. So Airtable is a place where anybody who I give a link to that can edit, they're kind of on the honor system to go in and like do only the section that I assign them to, but it's changing all the time. So we have this situation where we don't really know who changed what when, and it could be total chaos. So every now and then, I will actually archive it in query. This is what our company does, is have this data platform that also is a version control system. So by running a little script locally on my machine, I can pull down the data set as it exists at any given moment on Airtable with a little node script, and then make a commit of that data set to a query data set, and then push that up to Query Cloud. So I just run that command whenever I need to, and that gives me a new sort of snapshot of that data that is also published so people can download it. If you go to query.cloud and you see this capital projects data set, you can actually see when that commit was made and when it was updated, and trust it a little bit more because you know exactly what happened, and you can see the version history, which is wonderful. So we're using our own product for this, which is great. Airtable as my editor and Query as my archival site where I can store the data and trust that it won't be moved around or modified because it's an immutable version. So what's great is that now that I've shown you that we have this script that runs somewhere else, it's a good time to introduce where we're headed at Query with dataset automation. So this is a slide that shows our dream of datasets that update themselves. And what that really means is that there's a script that doesn't live somewhere else and run somewhere else, but actually lives with the dataset. And I mean that in a true sense that it's actually versioned along with the data. If the data changes or the script changes, it becomes a new version. Basically what that means is you can have datasets that can reach out on a schedule or on command and pull down source data to make a new version of themselves. And that's the way we've structured things at Query. In addition to that, datasets can be based on another dataset. So as long as the source is in Query, it becomes very easy to say, anytime this bulk dataset is updated, these ones are all listening for that event and can pull down the bulk data to update themselves. So what that would look like for this particular project is that we pull down data from Airtable into this FY 2021 capital projects detailed data set. And then there's 3 different users that want to consume that bulk data. This person may want to join it with neighborhoods. This person may want to filter it for Brooklyn, and this person may want to join it with demographic data. So each one of those processes in the normal data analysis world would have happened inside of a Jupyter notebook or in a script somewhere running on their machine. So what we're trying to do is elevate these common data practices to a place where they can be shared, trusted, and archived. Those derivative data sets may be useful to other people as well. So that's kind of the world we want to live in. You may have heard of us refer to this as the data commons in previous presentations, but that's where we're headed.
I also wonder if there's a way to see which projects use participatory budget process. So you could imagine someone adapting the data set and either adding a column to tag that. And then a second question, is there a way of telling if a project is completed? I look at local projects on a map and know where some are finished in X year or X fiscal year, some in process and others not yet started. I know this firsthand, but cannot tell if I only look at the info on your map. Maybe add something to that, like time period.
I think a big thing to know is that projects come in and projects fall off. As far as I know, anyway, anything that's in there now is planned to happen or is ongoing. And when it ends, like when it gets finished, it actually disappears, which means to really get a good picture of what's happened when over the long time span that you have to be looking at. And wherever you start looking, there's still going to be projects that began prior to that date. So it's a much bigger task. So really, like, that's a huge asterisk too, that everything that's on this map is what existed in the data set last fall. It's already changing this year. Every time the new budget comes out, there will be brand new projects, and there will be some projects that probably disappear. Even if we were to complete this current iteration of geocoding projects, there's going to be a handful more that come into existence next year that we have to continue this work. So you're never done. Or as they say, like, software is done like the dishes are done. Data sets are also done like the dishes are done, which means you'll be doing them again very soon.
Are you pairing projects to specific bonds in light of being tied to specific financial investment?
No, not that I'm aware of. The only thing that's in the data set is city funding versus non-city funding. So I think that's as good as it gets unless somebody has more detailed information sources for each of these. I think there are ways to find out more details about where the money's coming from. And I think in general, there's a lot of other things we could attach to these, like news articles, pictures, which would be wonderful. Like, people can just go out and take pictures of these capital projects. So that's another eventual goal of this website, if anyone's interested in it. Yeah, my vision for this website is that it become the source of all this information coming together. Whatever people can contribute is, I would love to be able to click on this, the carousel and Prospect Park project, and be able to see link to the contract, star rating for the contractor, a bunch of local news articles about how people are enjoying it or how they're inconvenienced by the construction or whatever it is. All of these things have different footprints around the community, and there's lots of information artifacts that we could put together for each one of these things. So this map is open source, so if you want to help out, it's on GitHub. We basically rebuild it, so it's a static site. There's no backend to it. Every time we update that query data set, I can just go to the website that's hosting this and just say rebuild, and it'll just go grab the latest from query and then put the website together. So we actually do that at the end of this session once we've added some new projects. So to give you an idea of where we're at, this is kind of cool because we started with like the handful that I geocoded personally back in like November. So we had 60 or 80 or something done at that point. After a bunch of people helped out on Twitter and just volunteered, we were able to get up to about 2010. So we've actually mapped 91% of the projects that have local reach because they have a community board mentioned, which is 39% of the entire data set, which is pretty awesome. So I think the next goal, I need to go through and actually figure out why we only have 91% when we've in theory touched every community board. And I think there's just a lot of projects that just can't be geocoded for whatever reason, because they're for things like vehicles or they're for things like computer systems and things like that. And then I think the next step is to actually do the borough-wide ones, because many of those can be mapped to a discrete location. We just need to make sure we're clear that considered borough-wide and not local impact, but they should still be mapped. So I think that's where we're going to start next.
Is the data verified in any way once it's geocoded?
No, that's another big caveat. I think we have a lessons learned slide at the end of this that would actually list that, but yeah. QA/QC is a problem. There's no real verification. So I think what I would love to be able to do is have the website be a place where you can just flag something and it'll just go into another Airtable somewhere. Somebody said that this isn't right, or maybe you can leave a comment for it. It's come up where somebody forgot to put a negative on their longitude, and it ends up, if you draw a line of latitude eastward to the opposite longitude, you end up in Uzbekistan. So we had a couple point geometries in Uzbekistan for a while until those got fixed. But yeah, I know some of these are in the wrong place. I've already heard complaints, some of them, especially like the sewer projects, but I think it's a best effort and we have to come up with some kind of plan for feedback on this. And actually in the meantime, the issue queue on Query Cloud is actually a great place to start. So you can leave a message there just like you would on GitHub, and we can use that as a place to track those kinds of issues.
And as we started moving into this realm of working from home, we started seeing articles such as these pop up by around the end of March and early April of last year, with due to COVID, subway sort of service cutbacks, all of these sort of working together in leading to these packed commutes for a lot of people. And so these are a couple of examples of pictures and videos of this happening on the subway around the start of COVID in New York City last year. And what we saw from this is, yes, trains were getting crowded, but this also affected people disproportionately. So as soon as we went into working from home territory, we were some of the more privileged people who had the opportunity to work from home. There were so many others who didn't have that opportunity. They had to continue going into work. And in New York City, the subway system is like the lifeline, and everyone uses it, and it's vital to get around. And what we saw is essentially communities where people are still working in person being more affected by this, having to commute in these crowded subway cars. But this wasn't just a conversation last year. We are continuing to have this conversation even now. And these are a couple of more recent articles published around this topic, around how we can protect ourselves and stay safe from COVID while riding the subway even now. And Times also did this cool article about looking at ventilation systems in subways and looking at how the distribution of crowded subway cars is across the city, and where are the people who still need to go to work using subways. This was the broad context. And it so happened, and the reason why all of this caught our attention was around this time, we happened to be working on a project using some open data from the MTA. Particularly, we were looking at accessibility on the New York City subway system. We had data from the MTA about descriptions of all the different elevators and escalators in the subway system. And we wanted to make this data a lot more easy to interpret for someone who might need to use elevators while commuting. And what came out of this is charts like these, where for a given station, this case, Columbus Circle at 59th Street, you can see what the different elevators are that connect you from the street level down to the different individual platforms for all the trains at the station. So we put this together and we were working on this, but obviously as COVID started spreading across the city and the focus around this shifted, we wanted to see how we can translate some of the learnings, this project around looking at different open data sets from the MTA into solving a different problem, which is a lot more relevant in the current context. So this is when we thought, okay, so how can we shift our focus of this project, and what are the sort of two main questions we would love to answer? So again, looking at all of these anecdotes about crowded subway cars, We wanted to see, okay, can we provide information about how crowded the commute might be for different folks who are still needing to commute? And there are sort of two ways of thinking about this. One commuter we think about is someone who has some flexibility in when they can commute. So it's not necessary that I need to go in at 8 o'clock, but maybe I have some flexibility around that time. So for those folks, it might be relevant to know, okay, given my particular commute, the trip that I take, what time might be the better time to commute? So when is my commute the most or the least crowded? But secondly, there are people who can't change their commute or when they have to commute. So for those folks, it's important to know, okay, along my commute at a given time, where along this trip does it get most crowded? So if I had the information, can I use that to better determine which trip or route I should take so as to avoid having more people along a trip that I'm taking? So these are the sort of two broad questions that we arrived at after thinking about this problem a little bit. And we hope that we would be able to answer these questions using open data that's made available by the MTA. So what is the data that's available? MTA actually publishes a lot of information. Firstly, we have information about all the schedules of trains. So these are the static and real-time data feeds, which tell you for all the different trains and buses, what are the schedules they're supposed to follow. And the real-time data also looks into what is actually happening in real time. And we'll go into both of these in a little bit. There's also other useful information. So where the stations are, how many people are entering and exiting the stations, and other sort of useful information around people and just the stations itself. And lastly, these are all sort of automated data feeds that the MTA has. But the MTA has also conducted a couple of interesting surveys over the last decade where they surveyed a whole bunch of people about their ridership patterns, asking them, okay, so what are the commutes you're taking? What time are you taking them? What's your exact route? And so on. And this, as we'll see later on, turns out to be very, very vital information in what we're trying to do. So we have all of this data and we have the questions. So what are we really trying to solve, right? So we want to know how crowded a train is likely to get. And we can think of this as, okay, so if we know when the trains are arriving at a station, and if we know when people are entering the station, then the task of knowing how crowded a train is simply linking these two pieces of data together. So we have the trains on one side, the people on the other side, and if we can connect these two and say, how many of these people are likely to take this train, then we can essentially say how crowded the train is likely to get at different points over the day. Sounds quite simple, right? But obviously, there are a lot more nuances to actually doing this, and we'll go through this process step by step. Let's start with the train schedule. So this is the GTFS data that I mentioned just a little while back. So the GTFS data is a global specification for how transit data should be made available publicly. And the MTA has these real-time and static updates of train schedules. So this tells us what the active trips are during the day, where the trains are located, and so on. And we've seen this data in action if you've taken the New York City subway at any point. The boards that you see on the platforms, which tell you how far away the train is, as shown as the example here. So this board is powered by the same GTFS data. So the data that powers these boards is made available publicly through an API, which we can use to get the same data, which tells us how far is a train from reaching a particular station? When does it actually reach the station, and so on? And this data, like I said, is available like real time. So this data can change like every minute. And what we're doing is essentially polling this API every minute to get this raw data. And this is around 1.5 to 2 gigs of data every day that we're dealing with, which is quite a challenge just in itself. And apart from that, there's also a few things that we need to do before actually making this data directly useful for an analysis. There's a little bit of cleaning, which is quite common with most open data sets. In this case, there's some nuances around how the starting time for each train is sort of indicated in this data, which we need to fill in and make some educated guesses about. And sometimes there's some missing information. So the feed might break intermittently and we might miss some information. It might be on the feed side, it might be on our data collection side, but we need to account for some missing information every now and then, which we need to fill in. But once we do all that, we get the information that we need around here are the trains which are operating at this moment, and this is exactly where they are. They arrived at this station 5 minutes ago, it's heading towards the next station, and so on. So this is the train side of things. So we know which trains are running and when. So the next question we want to look at is, okay, so how many people are commuting and when, so that we can link both of these together. The question about how many people are commuting can be answered by looking at our own path into the subway system. So whenever we enter a station, we go through these turnstiles. And every time someone walks in or out of each of these turnstiles, this data is recorded by the MPA. And this is made available as turnstile usage data. So this data is available at the end of each week. Unfortunately, unlike the train schedule data, this isn't available real time. So every Saturday morning, we would get an update from the MPA about how many people use the subway over the last. Secondly, this data is available for each entry and exit point. So each of these individual turnstiles data are recorded separately, which is great because that's useful knowledge in terms of where exactly in the overall station complex people might be entering. But this data is only available at an aggregate level. We don't know this, for every minute or every 10 minutes or 15 minutes. We know this for every 4 hours. And this poses a bit of a challenge because we know how many people entered any given station between something like 8 a.m. to 12 p.m. But the train data we have is more accurate in that we know exactly to the minute when the train arrived at the station. So given that these two are at different time scales, the challenge of making them both play with each other and be able to merge these becomes a little bit of a challenge. So let's look at how we actually try to solve this. Here is an example of Canal Street on the one line on this day last year, so 10th of March 2020. So the chart here shows time in hours on the x-axis and the count of number of people per hour on the y-axis. Those flat lines you see are essentially the 4-hour blocks where we are averaging these counts over those 4 hours. The orange line represents exits and the green line represents entries into the station. So Canal Street on the one line is down in Soho, which is predominantly a neighborhood with a lot of offices, which is why what we see is in the morning, so between around 6 and 9 or even 12 p.m., we see a lot more exits than entries. So these are people who are coming from all the different places where they live and they're exiting at Canal Street to go into work. And we see the exact opposite later in the day. So around 5 o'clock, 6 o'clock onwards, we see this big peak in the number of entries into the station. And these represent, all the people who work in this neighborhood taking the one line at Canal Street to go back home, which is why we see more entries later in the day. But in this case, when we're looking at a particular period of time, so say between 5 a.m. and 9 a.m., we are sort of averaging the counts over this period, right? So we have around 375 people exiting the station per hour, approximately. And we know just by looking at it, it doesn't make sense. Anyone who's commuted, we know that there are certain rush hours and people are more likely to take the train at certain times of the day and not really early in the morning. So zooming in further over here, just for this period of time, it doesn't make sense to say that the same number of people enter or exit the station in this case per hour all the way from 5 a.m. to 9 a.m. We need to do something a little bit cleverer here. One thing we can do is say, okay, maybe it's not equal over the entire 4 hours. Maybe it sort of continuously increases over this period of time. So fewer people are likely to exit from the station at 5 a.m. But then as the morning goes on, more and more people are coming into the station. So we can, instead of having a flat line, we can interpolate this in a more interesting way. But this isn't just one choice. We can do this in different ways. Maybe it's not this sort of straight line. Maybe it's a much slower increase early on. And then there's a particular peak time at which, more and more people are exiting the station. And then it plateaus closer to 9 a.m. So how do we know which is right over here and what's the best way to interpolate this information? This is where the ridership survey that the MPA conducted comes into play. So like I mentioned earlier, this is a survey of a whole bunch of people who are commuting using the subway, and the MPA has made the data available around all of their responses. So when are people taking the train in the morning? At what time are they entering at the origin, exiting at the destination, and so on. And what we see from that data is roughly the sort of percentage of people who are commuting at different hours of the day. And again, looking at this period from 5 a.m. to 9 a.m., we see what the curve generally is. So it's pretty slow from 5 to 6 a.m., then it picks up between 6 a.m. and 7 a.m., and it continues to increase, but at a slightly slower pace between 7 and 8 a.m., and then sort of slowly reduces between 8 and 9 a.m. And this matches our prior beliefs around what the rush hour on the New York City subway looks like. And we make use of this information now that it's available in a more quantifiable way to interpolate data that exists over a 4-hour period into much narrower time frame. So when we do that, the ridership at Canal Street on the one line looks a little bit different. rather than the picture on the left, what you get after interpolating is the picture on the right. And it's important to sort of see that the scale of data at different points is very different. So between 6 a.m. and 9 a.m., we saw around 375 people per hour on the left. But on the right, we see that this changes a lot. So between 5 and 6, it's like lower than 200 people per hour. But then between 7 and 8, this spikes up all the way to around 800 people per hour. And then it sort of drops down again closer to 9 a.m. And we see something similar on the entry side later in the evening as well. So this interpolation and using this information allows us to better estimate how many people might be commuting during peak and lean hours of the day. So it allows us to model rush hour commutes a lot better than we could without interpolation. We looked at when trains are running, and now we looked at from information that's available, figuring out how many people might be commuting and when over the course of the day. Now comes the tricky part, which is how do we combine these two pieces of information? So all of these people who are entering and exiting the station, which train are they likely to take? Again, I think a picture here says, 1,000 words. So you enter a station, you go to a platform, you still have a choice, right? So in this case, for the L train at Bedford Avenue, someone who's waiting at the station can choose to go towards Manhattan, or they can choose to go towards Brooklyn. All we know from the data is just how many people have entered the station. We don't know where they're exactly going. So we don't know individual choices here. So how can we figure out what choices people are more likely to make? To illustrate the process of thinking about this, it's again easy to look at an example. So here we have the G train between Brooklyn and Queens. And let's say you're entering the station at 4th Ave and 9th Street on the G train. So now you have a couple of different directions in which you can go. So towards Brooklyn, there are 4 stops, and towards Queens, there are 16 stops. So one way of thinking about this might be, okay, if there are more stops in one direction than the other, then maybe that's the direction in which people are more likely to travel in. But I think we can do a little bit better than this, because it's not obvious at all that this is the best way to do it, because the G train, for example, provides a very important point of connection to a lot of other lines at Church Avenue. So if people are looking to take the G train and transfer over to the A, C, or the 1, 2, and so on, it actually makes more sense to travel towards Brooklyn to Church Avenue and transfer over there than in the other direction to Queens. And this is where, rather than just looking at how many stops are there in each direction, we can look at how many people are exiting at these stations in each direction. So if we know that there are more people who are exiting from these stations in the Brooklyn direction than the Queens direction, then we know that someone who's entering at 4th Ave and 9th Street is more likely to go towards Brooklyn than towards. So let's take a moment and look at how this works in practice a little bit more. So again, let's say you're at 50th Street in Manhattan at 8 a.m. You enter the station and you have 2 choices. You can either go uptown or you can go downtown. In fact, those are not the only 2 choices. In the uptown direction, you can either take the C train or the E train, and likewise in the downtown direction. So how do we know how likely someone who's entering 50th Street at 8 a.m. is to taking each of these trains? So looking at the exits in both of these sort of directions for each of these trains, we can see that between 8 and 9 a.m. on the uptown C train direction, we have about 45,000 people exiting from all of those stations along that route in the uptown direction. But in the downtown direction, we see around 95,000 people exiting from stations along the route of the C train. So looking at this, we know that, okay, so then someone who is taking the C train at 50th Street is maybe twice as more likely to take the train in the downtown direction than the uptown direction. Now we can add in more information about the E train as well to this. So on the E train, it's quite interesting where we see roughly the same number of people, exiting stations in both directions. So we know that, someone taking the E train might be equally as likely to, go uptown versus downtown. And combining all of these pieces of information, we can compute individual sort of probabilities. How likely is a person to take a given train at a station? So in this case, we arrive at looking at the ratio of these exits, about 14% probability that someone would take the uptown C train, while having a 36% probability of taking the downtown C train. And then for the E train, we see that the probabilities are equal at 25% likelihood of taking either uptown or downtown. Sort of these probabilities for taking a particular train at a station can change over the course of the day. So this is looking specifically at 8 a.m. But we do this for each hour of the day to compute what these probabilities are at each station for each and every line at that station for each hour of the day. And this is what we'll use to compute how many people might be entering and exiting from the trains at any given station. We've answered all the questions leading up to the main one, which is how crowded does a train get over its route. So let's look at how that computation happens. So continuing from the same example of 50th Street at 8 a.m., we saw a 14% probability of taking the Uptown C train. So now let's say for illustration, we know around 100 people have entered the station at 50th Street so far, and they're waiting for a train at 8 a.m. Let's say the Uptown C train arrives at 8:01 a.m. So it pulls into the station, there are 100 people waiting. Given our numbers that we just calculated, we know that there's a 14% chance that a person waiting at 50th Street at 8 a.m. might take this Uptown C train. So from this, we know that 14 people might enter the C train at this point at 8:01 a.m. But because we're computing this with all the information already available to us, we can also see how many people might be exiting the station at this point. Over the next few minutes after the C train has arrived, say at 8:05 a.m., we know, okay, between then and now, about 4 people exited the station. So now we know this is the only train that arrived at 50th Street. So we know these 4 people would have come from the C train. So the C train that comes to 50th Street, 10 people entered and 4 people exited. So the occupancy on this Uptown C train went up by 10 at 50th Street at 8:01 a.m. We also know that from the 100 people who were at the station to begin with, 14 people entered the C train. So we're left with 86 people now waiting at 50th Street for the next train to arrive. And that 86 would become the sort of number which we multiply each of the probabilities for all the trains to compute how many people are likely to enter the train. So we've now gone through the sort of entire process of going from the data to combining these pieces of information together to computing how many people are likely to be on a train or travel by a particular train at a particular stop at a particular time. So putting all of these pieces together, we can look at what these crowds have looked like over the past year. And what we have here is time on the x-axis and the sort of percentage of crowd on a weekly basis relative to what we saw before. So the part on the left represent like the times before COVID. So this is when all of us were commuting by trains every day to our work and other places. And we see that back then we had a large number of people traveling by the New York City subway system. And this changes a lot, obviously, as soon as a lot of us end up staying at home and working from home, where ridership levels drop. And subsequently, the crowd in the train drops significantly in March. Next, we see a sort of steady growth in these numbers around June, July. This corresponds to the 4 phases of reopening that New York City went through. And this is when we see a sort of uptick again in the number of people who are commuting using the New York City subway and subsequently the crowds going up. And following this, we also see this sort of extended summer periods. As we recover from COVID and as the situation in New York City started to stabilize and improve and more places started opening up, and thankfully we had a long summer before we got hit by a rough winter as well, we saw ridership continue to sort of increase and reach its sort of maximum between September and October of this year. Lastly, we see what the levels are right now. In 2021, as of now, the ridership levels are about 30 to 40% of what it used to be before COVID. And interesting to note this one little dip that we see in 2021. This actually corresponds to the 2 big snowstorms we got hit by at the end of January, around early February. So it's pretty cool that we can see the impact of that on, how crowded the trains were around that time as well. But this sort of overall picture doesn't tell us the whole story. So we might look at this and say, okay, the ridership levels and the crowd in a train might be around 30 to 40% of what it used to be on average. But this changes quite a lot over the course of the day and by direction. And this is something that we might be familiar with. So what we saw earlier with Canal Street, for example, we see that for a lot of trains in different directions. Here we are showing the crowd on the 6th train by hour of the day, with the Manhattan-bound direction in orange and the Bronx-bound direction in green. And we see that the Manhattan-bound train is more crowded in the morning between 6 and 8 a.m. This is people going into Manhattan for work. And we see that the numbers later in the evening between 4 and 6 or 7 p.m. is greater in the Bronx-bound direction. And this is representing people heading back home after a day of work in the evening. And all of these numbers are what these estimates look like after the stay-at-home order. So looking at from April 2020 onwards. So while the larger picture tells us, okay, it's only about a third as crowded as before, it's important to note that this is actually, the complete picture is very different in that this can be very different in the morning rush hour and the evening rush hour, where it can be a lot more crowded than that. We can also use all of these computations to look at how this looks like over the course of a day across all the stations. So here on the map, we have all the stations marked out, and the sort of color of these dots change based on how crowded each of these stations get over the course of the day. So starting at 5 a.m. all the way up to 10 p.m. at night, with lighter colors representing that it gets more crowded, and darker colors representing times when it's less crowded. And we've heard of the New York City subway system being the heartbeat of the city. And in this sort of animation, you can almost see the heart beating in a way, where people come in and it gets crowded in Manhattan early on. And then over the course of the day, by later in the evening, it sort of eases back out as people head back home. And while this gives us a good sense of what the commuting patterns look like over time and spatially, we can zoom in a little bit further at different times and get a much clearer picture. So this is the same chart, but instead of an animation, we are only looking at between 6 and 7 a.m. in the morning across the city. And what you see is very interesting. So yes, it seems like there are a few lines in Manhattan where it's getting crowded, but we also see that all of these lines are getting crowded much earlier. So for example, up in the Bronx, the 2 and the 3 line, or the 4, 5, and the 6 line are already fairly crowded, or as crowded as it is in Manhattan up in the Bronx. We see the same thing with the 7 line in Queens, the same thing with the M or the Z and the J lines in East Brooklyn, and the NQ and the D, all of these lines in South Brooklyn. What this represents is that all of these lines, yes, they are pretty crowded when they reach Manhattan, but they're crowded much earlier on. Most of the people who are commuting from these outer boroughs, namely Bronx, Queens, and Brooklyn, early in the morning. We continue to see this later in the day as well. Instead of looking at early in the morning between 6 and 7 a.m., if we look at this in the evening between 7 and 8 p.m., what we see is while the trains in Manhattan are not as crowded right now, we continue to see relatively higher levels of crowd in all of the same points that we highlighted before, in the Bronx and the Queens and in Brooklyn. And this clearly represents the fact that a lot of people who are having to commute during this time continue to be largely from the outer boroughs. And a lot of work has been done to show that this picture represents those who are having to work, and people living in the outer boroughs on average represent people who earn less income or have lower median incomes. And these are the people who are continuing to having to commute over the course of the day. And we see that through this picture in the morning and in the evening, with trains getting crowded up in these areas a lot earlier, and then during the evening rush hour, staying more crowded in these areas later in the day as more people are returning home at these locations. So this ties into what we saw in some of the reports earlier, where the crowded subways are affecting people disproportionately. And while we have a lot of qualitative insight into this before, by doing this analysis, we can look at this in a more quantitative way. So we now have numbers attached to this from these estimates of how crowded the trains are at any given point, at any given time in the day. These are sort of high-level insights, right? And this is useful to get a picture, but obviously this doesn't fully answer the 2 questions that we set out to. And the 2 questions, circling back to that, is how does my individual commute, looking like with respect to crowds over the course of the day and along the route? Global insights are useful, but end of the day, people who are having to commute are looking for more personalized insights into their respective commute, which is why we took all of this analysis that we did and we put together a tool, SubwayCrowds, which I'll give you a demo of in a sec, but it looks like this, where every person can put in their individual commute that they typically take and look at the same piece of information. So how crowded does it get over the course of the day? Where along the route is it most crowded, and so on. Now, without further ado, then I will jump into the demo of this. So the tool is available at subwaycrowds.dsdataclinic.com. And when you go to the site, this is the first page that you'll see. I'm going to enter in a commute that I haven't taken in over a year. So this is my typical work commute, taking the 1 line, getting on at 79th Street, and then getting off at Canal Street in the morning. So once you do that, you get these 2 plots. So there are a few things that I want to highlight here. So for a given trip that I've chosen, the two plots we see are how crowded does this trip get across different hours of the day. And then here we see how crowded does this trip get for a given hour at different points along its route. There are two things that we did apart from estimating these crowds. So first is, rather than showing, as we compute this information, we compute this at the level of the train. But obviously a train typically has about 8 to 10 cars. So the numbers that we show here represent the maximum number of people that you might encounter in an average subway car over the last 2 weeks. So let's break that down. I am taking the one train at 79th Street, let's say at 8 a.m. So along the route between 79th Street and Canal Street, what is the maximum number of people I might encounter on an average subway car? It might be right at the beginning, or it might be as the trip goes on, more and more people enter the train, and therefore that's when I'm more likely to encounter a greater number of people. So this gives you a picture of roughly what's the maximum level of crowd I might expect on this trip at this time of the day. We also average this over 2 weeks. So this is to account for any bumps that we see in patterns. So for example, as we saw with the week of the snowstorm where ridership dropped significantly, we don't want one-off events like that to influence these sort of estimates a lot because we want to provide a slightly more general picture of what the trend looks like. So rather than looking at this data just for a particular week, we average this over the last 2 weeks. And here we see 3 lines on this chart here on the left. So the blue line here represents what the level of crowd looked like a couple of years ago. In fact, just until last week, the tool used to say 1 year ago. We are just now about hitting the 1 year anniversary of us moving into working from home and the shift in our lives. So now this represents what the numbers were 2 years ago, just to give you a sense of how crowded this trip used to be when we all used to commute every day. The yellow line here represents what these numbers look like right now, so over the last 2 weeks. And the darker black line here represents what it looked like a month ago. So both of these have to give you a picture of, so this is what it is now, and this is what it was a month ago. So you get a sense of how this is trending from last month to this month. And this is again useful information potentially for someone to keep in mind as they are thinking about commuting. Is the crowd going up every day or every month, or is it on a downward trend? So this is what we see on the left. This is telling you the number of people per subway car for a trip over time of the day. So you can slide this around and say, okay, what does it look like at 8 a.m.? What does it look at 9 a.m.? And you can see that, okay, if you do have some flexibility in your commute, I might say, okay, it looks like the train gets relatively less crowded after 9 a.m. So maybe if I commute somewhere between 9 and 10 a.m., I might likely encounter fewer people on the train. So if I do have some flexibility in my commute, I might be able to use this information to choose when it is probably easier for me to commute, having access to now this information about how crowded the train might be. And this is an individual decision, right? So each of us might have our own constraints as to when we can commute and our own sort of preferences for in what sort of condition we want to commute. And we hope that this information provides the context that one might require to make this decision. So then apart from this chart here on the left, we see this on the right, where for this given trip, so getting on at 79th Street and getting off at Canal Street, so all the stations along this route, and we see how crowded is the train at each of these points in time. And so for any given time that you choose, you can see what these numbers look like. So 8 a.m., which is when I typically used to commute, what we see is trains are already pretty crowded by the time they get into 79th Street. But then as time goes on and people get off at Penn Station and Midtown and 23rd Street and so on, the number of people on the train gradually decreases. And this is true right now as well, where at 8 a.m., what is the sort of average number of people that you might encounter in a subway car at each of these stops? And we're hoping that this information provides a valuable insight for someone, where looking at this, you might say, okay, so it is pretty crowded till Penn Station. So maybe I can switch my commute where I get to Penn Station through some other way. And then after Penn Station, I continue traveling on the one line because it gets less crowded after that. And you can choose different options. Here we're looking at the one line, but we can go and see how it looks on the express train in the same direction, where if I get on at 72nd Street and look at how crowded it looks getting to Penn Station, we can see that the express line is a lot more crowded. So perhaps it might not be the best option to take the express instead of the local line. Having this sort of comparison allows you to say, okay, maybe the best decision that I can make at this point is to maybe stick to the local rather than potentially taking the express train at this time. So apart from these two charts, just want to highlight a couple of things. So we made it easy for someone to toggle the direction that you're traveling in. So if I want to quickly look at what this looks like in the evening, I can just toggle this and say, okay, so what does this look like from Penn Station to 72nd Street over the course of the day? And we can also see how it looks like on a typical weekday compared to a typical weekend. And we see that the typical weekend commute looks very different from a weekday commute, with totally different patterns that we see in how people commute over the course of the weekend. This is an overview of what the tool looks like. We have an option for you to give us feedback on this, and I would urge you to do that. And there are a few links in there where you can share this with others so that those who are commuting can make use of this information to help their day-to-day decision-making at this sort of critical junction in our lives right now. Now that we've seen the tool, I just want to address quickly some of the caveats and limitations to this estimation. So we saw that the data that's available around turnstile usage is available each entry point, so for each individual turnstile. And some turnstiles in stations actually lead to different parts of the station. So there might be certain turnstiles which only lead you to the uptown direction in the station, and others lead you to the downtown side. But unfortunately, this information about the mapping between individual turnstiles and which platform they lead to wasn't yet available as we started working on this project. The MTA has been developing this for a lot of the accessible stations to begin with, and we hope to have more accurate information about this mapping between turnstiles and the platforms in a station over time. And this would improve our estimation methodology as we know, okay, all of these people who are entering this particular turnstile are only going in the uptown direction, and therefore our estimates for those trains would get a lot better. The other major challenge is how do we account for transfers within stations? And this is a particularly difficult challenge because the only insight we get is when people enter and exit a station. We don't really know how people are moving about within a station, especially at big hubs like Times Square and Penn Station and Atlantic Avenue, Barclays Center, and so on. You would see a lot of people getting off, say the 2 train and getting on the R train or something like that. And we don't know this because they're not exiting the station at any point. So it gets a lot difficult for us to estimate how likely someone is to transfer at these stations. And this is where we might look at a slightly different approach, looking at the sort of graph of all the routes and the entries and exits at different points to compute what the flow might look like, including transfers. And this is a slightly different way of thinking about it, which we have now started working on, but would love to flesh it out a lot more to better capture transfers and thereby better estimate how crowded a train is likely to be. Lastly, I want to just highlight that these are estimates. We saw all the steps and the assumptions that we had to go through to compute these numbers, and we tried our best to do a lot of spot checking and validate this as best as we can based on our own commutes during this time and what we know of from back when we used to commute. But obviously, we would love more help from you all to use the tool and look at, as you commute, what the numbers look like, and let us know your feedback on the feedback form on the app, where you can let us know whether the information for a particular trip, did it look good, or did it underestimate or overestimate the numbers a little bit, so that we can further fine-tune our methodology based on feedback from all of you. And secondly, all of the work that we have done with this project is completely open. So all the code for this is available on our GitHub, and we are working, like mentioned here, on some of the ways of making these estimates better by taking a slightly different approaches to capture some more nuances that we aren't fully capturing currently. And we'd love to get your help to build some of these next steps out on the tool as